Are we here? Well, not so many. While I'm preparing, our usual few academic minutes. Think if you have questions. Did I send you lecture 16? I think I did, right? Do you remember? Did you receive the lecture yesterday? Hello?
No, I haven't received it. I think you only sent the assignment yesterday.
Oh.
Yeah, I haven't received the lecture yet.
Yeah, it seems. Good. I normally do it immediately, so I don't understand. It didn't. Okay, let's do it immediately. Is it good that it was open? But too bad, because actually I wanted you guys to have a look. Lecture 17. Let me see if you received the. I'm on the list, so that way I can know. Yeah. Okay, so that's okay. So I'll start unless you ask questions. Still give you a minute. Just to be sure. In case you woke up late like me. Okay. So we go on with the neutrino mass. And today I'd like to speak of left-right theory. But most important is the message, which is the seesaw mechanism.
Excuse me, Professor. Are you sharing your screen already?
Oops. Maybe I forgot, right? I did. Thank you for reminding me. Oops. So this is what I want. Is this what I want? So we wanna go on with neutrino mass. So what we said yesterday, there are strong indications that we have to focus on the origin of parity violation. We found out that the electron mass being non-zero is deeply connected through the Higgs mechanism with the parity violation. It's very hard to understand how this would work but neutrino mass being non-zero is crying for parity. So we said, look, why don't we just break parity, break through spontaneous? And I just giving you as a principle, if you need a symmetry and you need to break it maximally, but still it serves to you, that's what Nambu, Goldstone, Higgs, and others taught us. Do it spontaneously. And that was very clear. We should start with the left-right symmetry group. SU to L cross SU to R cross U1, which, by the way, preceded experiment by a long shot. Okay, we are talking of 1974 to 75. Developments through the works of Parity, Salam, Mohapatra, and myself. It is interesting that Salam played a fundamental role even in this particular opposite direction from the original work. Remember, Salam started with, it's Salam, not only one of the developers of the standard model, but the left-handed neutrino is the work of Salam. In 1957. He always has a deep regret that he only thought of neutrino and not of the other fermions. Okay, this was for neutrino. Of course, the great work, more complete, was Marshak and Sudarshan. In particular, the Feynman and Gell-Mann. Remember Feynman and Gell-Mann? We speak of 57 to 58, who suggested that all fermions are left-handed. And Marshak and Sudarshan actually showed that this was necessary in order to be in agreement with experiment, even suggested that some experiment must be wrong, and they were prophetic. And he would be, Salam, one of these people that we'd call the Li Yang dream to restore parity. So we are restoring parity. In this theory, parity is a good symmetry. And I was told yesterday that all I have to do is take the left and right fermions as doublets. So see, if you get this idea, and this was the curse in the beginning because people were sure that neutrino is massless. If you like the idea that there is a left-right symmetry that we call parity, you predict immediately neutrino mass is non-zero, and you have to live with the consequence. To me, that was actually beautiful. I found this possibility somehow so natural that the world should be left-right symmetric. I'm still puzzled why people work. I'm always amazed that my peers and my colleagues and my students work on very, very complicated symmetries, but not on the most obvious. Then, of course, who cares? I don't want to convince you that this is a true theory. I want to tell you something that's sort of the Feynman approach to physics. What Feynman says, which is very beautiful. I don't care what your guess is. Feynman says, make a guess. And you don't even have to justify it, okay? And then show me that you can compute, make predictions, and compare with experiment. If you cannot do that, please shut up, okay? And don't tell me that it's very hard and then keep asking me to follow you year after year. So this is what we have to do. This is what people did in the standard model. Why am I bugging you with this? Because you and I have to understand the origin of neutrino mass. And since this is the original theory, in other words, the reason I'm bugging you with this, not because I worked on that, it's the other way around. I worked on that, and I still do these days. I came back, I'll tell you why in recent years. Because this is the original theory of neutrino mass. Just like the standard model was the theory of the Z boson mass and W mass, this is a theory that preceded experiment. So how does it work? Let's understand first, how can this be true that the world is left-right symmetric? Experiment says that parity is broken maximally. So how do I reconcile? How can I have left-right symmetry equivalent with maximal parity violation in H? After all, left-right symmetry is parity. Who can help me from what I've written here? Why does it agree with experiment? The answer is simple. I have left-handed gauge bosons here, the three of them, but I have also right-handed gauge bosons. In other words, in this theory, if there is a W boson, we have to call it WL. This is the guy that couples to left-handed fermions. There must be also WR, coupled to right-handed fermions. If there is a Z boson, it's not purely left-handed. But maybe just because the group is SU2L, let's call it ZL. It couples, of course, to the Z current, okay? So I don't want to say, remember, it was not completely left-handed. There must be also a new heavy, which will couple to the new current. And why do people say that parity is maximally broken? So in other words, P maximal simply means that MWR is much bigger than MWL. And MZR is much bigger than MZR. It's not a big deal. Just like any new physics. We believe that there are, there can be a plethora of new theories beyond the standard model, and the principle is always the same. So what we have here is a generic principle. So I'm giving you a hint how you do physics beyond the standard model. We won't speak too much. We will go to neutrino. This is what our task is here. I'm teaching the standard model, but the generic principle, you have some new gauge group which breaks down through some new Higgs to the standard model gauge group. This is the idea. That of course then breaks through the phi of the standard model, our beloved doublet, down to U1 electromagnetic. Remember, in the standard model, the masses of the particles, MW, MZ, and M of the fermions. By fermions, I mean quark and electron. All of these masses, all of them all the usual particles are proportional, all these masses, to the vacuum expectation that, let's give it a name, I used to call phi, the standard model doublet, right? That's the Higgs mechanism. That's the beauty of the standard model. I'm very sorry, I have an important delivery, so just bear with me 1 minute. Sì. Va bene, grazie. So this is what you know in the standard model. Now, if you have a new theory, then you have a new particle. So if some G new group, and there are new particles. So let's call it the mass of the new particle will be by the same logic proportional to the vacuum expectation value of phi nu. You agree? By the same logic. This is, you're going to repeat the Higgs mechanism. This will be the new Higgs mechanism. You see how you build the theories of nature? You just imitate the original theory that worked well. So Glashow said, I'm going to imitate the QED that worked beautifully. So I will assume also that the weak interactions are a gauge theory. Well, it required some more work. But finally, will be the Weinberg and Salam. And now, for us, it's even easier. We know that the Higgs mechanism works, so it's only natural, okay? And this has been the road that basically everybody has taken. Based on your belief, you choose your new theory, and you choose your new Higgs, and you get to the... So now help me, what are the new particles in this theory? In the left-right theory.
The SO2 right gauge bosons.
Oh, very good. WR plus. Let's write them down. WR minus. And the ZR, I called it for the lack of the better name. Is this all? Let's go back. Look at it here. Here. What else is new?
You are. Me too. Right, me too.
Right. There is another new particle. Okay, very good. Let's not forget it. New R. This is also new. And this is a crucial thing, by the way. There is a new Higgs. I don't want to bug you now with the new Higgs. The point here, the fundamental point, it's not just the new gauge bosons. There is also new R. New R is not the standard model particle. It's new. So it's not surprising that new R also gets the mass, and we have to talk about it now. I gave you homework to think about the new R, but obviously the homework is just a recapitulation of what I'm actually telling you. Part of the homework is you working out some details. Part of you is making sure that you follow the lecture. I like always the part which should be trivial if you follow me, and the part that should be an exercise. Before I do that, though, let's go back here and let's do the following. Well, why don't we write once again, maybe, so that I don't have to write once again G left right. Maybe this will be nicer to write again. Is SU2L. across this U1, nu, and there are coupling constants that we could call GL, you agree, GR, and we could call this G prime was the standard model, so how should I call it? I don't know, G bar. I don't know, sort of. Now, what is the idea of left-right symmetry? Remember, we said that by definition, there is a symmetry between left and right, which we call parity. Maybe I shouldn't write so small letter, I'm sorry. This is parity. That means that these coupling constants are the same. This is the idea of left-right symmetry. So I will call this identically G. There are two coupling constants, G and G bar. It just says the standard model. It's not worse. And remember the once again, the particle spectrum. Is this. So what about electric charge? Well, it must have T3 because we are inside SU12. But because of left-right symmetry, the left must be equal to right. And it must be the new hypercharge. I call it Y bar. The associated. I called Y. The standard model, so I don't want to call it Y. Now that I chose bar, I call it bar. So if I ask you to check, did anybody check what is Y bar?
Yeah, for the right, the left it's -1, and for the right it's 1/3.
For the left, well, we cannot say for the left, depends, quarks and leptons is different. So let's do for UDL. Well, it must be the same for left and right, you agree, because of left-right symmetry. So both UDL and UDR must have the same hypercharge, which is?
-1.
No. Quarks. These are quarks. Let me just write nu EL, nu ER, you are right. Y bar is -1, thank you. It's very easy, I just looked the formula of the charges. After all, the idea of this formula, let me write this formula. I guess for me, that's the now most fundamental formula. What I mean by this formula that Y bar is 2Q minus T3L minus T3R. So I just read. So for example, how do I work? I take UL, for example, and I say Y bar is 2. What is the charge Q of UL? And the same, of course, for UR. What is the charge?
2/3.
2/3. T3 is +0.5. Whether it's left or right is the same, of course. We did it in the standard model, by the way. It must be the same as in the standard model because they are doublets. And this is what? This is 1/3. 2 times 1/6 is 1/3. So you see, Y bar is 1/3. You see the advantage of the left-right symmetric theory, that the left and right are the same. So it's going to be very easy to remember that. So look, this is for quarks. And this is for leptons. Can you recognize what Y bar is physically? What is Y bar? In the standard model, it was a terribly ugly number. We couldn't give it a physical interpretation, but look at the difference here. Let me ask you, what is the baryon number of a quark? Let's go back to basic. Let's step back. Sorry, let's write like this. In order to answer that, let's step back. Always. Sorry, tell me again. Someone said something? Baryon number of a quark?
1/3.
1/3. Why? Because there are 3 quarks in the baryon. Because baryon, like proton, neutron, etc., is 3 quarks. Thank you. What is a lepton number of a quark? Well, it's a 0. Quark is not a lepton. What is the baryon number of a lepton? Well, it's 0. Leptons are not baryon. What is a lepton number of a lepton? Well, it's +1, right? So these are quarks, and these are leptons. I mean, this is trivial. But notice, but we have here, so let's write it here to help us. This bar on the quarks is 1/3. And on the leptons is -1. So can you read it from here?
So it's baryon number minus lepton number.
Yes. Now you can remember it forever. So although the theory is more complicated, there are more gauge bosons and there is more Higgs to study. So you can say, oh my God, I don't want a theory which is more ugly. Actually, it has one immediate, the idea of left ray matter brings you one immediate beautiful thing. The hypercharge of the left right symmetric theory is B-L. So we write, in other words, we write the Q electromagnetic is T3L plus T3R plus B-L/2. And this will help you because you can this way remember the standard model hypercharges. After all, you know that this is equal to T3L plus hypercharge over 2. This is the fundamental left-right standard model formula. This is left-right. So all you have to do is to remember that y over 2 is T3R, which is obvious, plus B-L/2. This is why it is ugly. In general, because you break the symmetry in the standard model, and therefore the hypercharges of the left have nothing to do with the hypercharges of the right, and you have to think, well, you can always do that, okay? So this is sort of nice. By the way, B-L, you know, I should have said, but this is obvious, okay? Better late than never. When we are stopping back, just a reminder, in the standard model, baryon and lepton numbers are accidental, we say, global symmetries. We didn't engage them, but they are still symmetries. How do I know that? Well, because what I have is quark can only turn into a quark, and lepton can turn into a lepton. There is no interaction that breaks this. There is no interaction that they can take quark into a lepton. This is kind of trivial. And remember how it looks like, just a reminder. All the interactions look like this. There is a photon which couples like this. Look, fermion. Fermion becomes a fermion. Same fermion obviously conserves B and L trivially. There is a Z boson. Again, the same. Who else is there? There is a W boson. That takes up quark into a down quark and neutrino or electron into a neutrino, as you wish. Obviously, again. Well, there is also our Higgs guy that couples as fermion, and the coupling is M fermion over MW. It's just not so important that obviously, again, fermion becomes, again, baryon and lepton numbers are, of course, good symmetries, okay. This is very important. So in other words, if you have baryon and lepton number, that means that these are two symmetries. I can write like this. Instead of talking of baryon and lepton number, I can talk of B plus L and B minus L. There is something called anomaly. Did anybody ever tell you anything about anomaly? No. In the field theory course, you didn't talk about anomaly. Right? Okay, just for those of you that want to know, you can talk about this symmetry has an anomaly, whatever that means, it doesn't matter. And B minus L is special. If you don't know what anomaly is, just forget this word. It's anomaly free. Let's put this into parentheses. In case someone knew something. So it doesn't matter. B minus L is a gauge symmetry in our left-right symmetric model. It's gauged. Okay. The point is, the fundamental point that this is the homework that you're going to work out, okay? The what else do I want to say here? I don't want to say much. Oh, by the way, the thing that is maybe here to keep in mind when I say the left-right symmetric theory, let's just write it down. This will be the only thing we should need, you and I, that if there is an interaction G over square root of 2 W mu plus I have to write now L. That means that there must be a new interaction. It's true that there are new gauge bosons, but the fundamental gauge boson like W, it's very easy to, you don't have to remember anything. All you have to remember that, remember the idea of gauge theories is the interactions are symmetric. Spontaneous symmetry breaking just gives the masses, but the interactions are symmetric. In the standard model, the interactions possess SU2 cross U1 symmetry. Spontaneous breaking, remember, okay, this is what I'm just reminding you, interactions respect original symmetry, which in this case is G left, right.
Sorry for interruption. I think you wrote DL in the right symmetry. Should be DR, right?
Maybe it's better to write R, you're saying. Thank you. You see, thank you, of course. I wrote something. This is whenever you write a new theory, doesn't matter what it is, the interactions will respect the symmetry. This is very important. Keep in mind this, all. And that helps you a lot because you don't have to remember it, okay? All you have to know the symmetry that you have in mind. Okay, and then we said now, what it is, what does it imply for neutrino mass? This is what we need to study. Neutrino mass is non-zero, but let's now study it. Any questions here before I embark on this? I'm doing this very pedagogical, as you can see, or I think I'm doing this very pedagogical. I'm trying to be. I'm giving you time. I'm reflecting. I'm posing. Okay. What we said, the crucial thing is this: we said that nu R, this is very important, is a new particle. What are the quantum numbers under the standard model gauge symmetry? When you have a new particle, now you study it. We must study it under the standard model gauge group. We have to understand it. When you learn new physics, please, this is often you go to seminars and you see people using very complicated language of new physics. For example, people say, I'm working on a string theory and then use the language of string theory. That is not good. It would be really bad if I now started to speak Spanish or Italian. Well, some of you will understand Spanish or French, and I'm sure some of you speak French. But I shouldn't do that. I speak other languages, okay? But it's not good that I use the language that I speak that is not your language, okay? We have a sacred duty when we study new physics. We must go back and do whatever we do, if we are doing an honest to God work, to discuss it under the language of the standard model, because by the way, this is the only physics we have. Everything else is speculation, okay? So what is it? Tell me, what are the quantum numbers of nu R? Okay, nu R under SU2L. In other words, the generators TIL, how do they act on nu R?
It's just zero.
Zero, yes. So we say that this guy is a singlet of SU2L, very good. What about the hypercharge?
Zero.
It's zero. How do you know that the hypercharge is zero very quickly? Without looking back into the formula of the left-right theory?
Because TR mu.
Well, that you have to sort of cancel it. There is a better way. When you have a new particle, forget the original theory. Just look at the standard model language. That's better. Q in the standard model is T3L plus hypercharge. You agree? But we just said that T3L is zero. So Q is Y over 2 for nu R. But Q is zero. Why? How do I know that Q is zero? Well, look, I go back. That's trivial. It's the, this is how it acts. It's the analog of neutrino, which is neutral. Photon is left-right symmetric. But okay, you can see it also from the generic formula. I think this is not wrong. It's just that this is yet reassuring it. So nu R, we say, is a singlet of standard model. Now, what I said yesterday, okay, let me say it once again. I said in quantum mechanics, there is a very easy way of writing a spin zero state. If I have a spinner, let me call it U. It's a two-component spinner. It could look like this. Then the singlet, the spin equals zero state, can be written like this. It's good that you are checking me. I make mistakes from time to time. This is U transpose. We can write I sigma 2, the antisymmetric tensor. And this is U. This is invariant. This is spin equals zero state, as we know. But if UR is a right-handed spinner, remember in our conventions, this can be written as like this. The right-handed spinners are the lower component, and therefore UR transpose I sigma 2 UR is a Lorentz invariant. Why? Because UR, just to remind you, transforms as e to the I sigma over 2 times theta minus I phi UR. This was rotations, remember? These were boost. So from the point of view of the invariance, I can write, no, I can just write like this. It's very easy to see. From it, it follows that UR transpose I sigma 2 UR is invariant, just as in quantum mechanics. Because theta minus I phi is complex, but transpose doesn't care about that. So please show this. It should take you 2 minutes. If you didn't follow me up to now, you must be able to do it yourself. But that I can write like this. Nu R transpose C nu R. Remember, nu R is a 4-component spinner. Please look here. Is nu R transpose. What is C? I gamma 2 gamma 0 nu R, which is nu R transpose. What is I sigma 2 gamma 0? Let's write it 0 I sigma 2 minus I sigma 2. Let me be boring, but I want to get you once again. I'm repeating it just to make sure. No, sorry, nu R. So this is 0 UR transpose. And what is this? This is I sigma 2, 0, 0 minus I sigma 2, 0 UR. This is UR transpose minus I sigma 2 UR. But this is invariant. It's just a minus sign of what we wrote above. In other words, I can write like this, M. I will call it MR. Nu R transpose C nu R is a Lorentz invariant but also the standard model gauge group invariant term, because nu R is a singlet. This is the famous Majorana master. (1937). Before disappearing forever, a young man, Ettore Majorana, takes a boat from Palermo to Napoli in March of 1938. Majorana disappears forever. He's only 32 years old. He was an unparalleled genius, according to everybody. He was the member, well, actually not a member, because he was a loner genius who didn't need anybody in the famous Fermi group. If you ever go to Rome, please, if you go to Rome, take a walk in Via Panisperna. It's a little street not far from the center. There was the Fermi Group Institute. There is a beautiful film, Boys of Via Panisperna. It's amazing. In this little building, you know, there was one of the best groups ever created. Okay, a number of them got Nobel Prizes. Ragazzi in Italian. One stood out, Ettore Majorana. And he finds the thing that Dirac didn't notice. He was only thinking about the electron. We talked about it yesterday. A beautiful thing that violates a mass term. Your homework is to work out details of this in the 4 and 2 component language. So you do the homework to grasp it better. And then we can meet again for an extra discussion. Any questions here, please? Okay, so look, let's just look at this right-handed guy. We said because it's a singlet, I can write this mass term. But let me just remind you, MR is proportional to the new Higgs vacuum expectation in a left-right symmetric theory. It's not just that it may happen. This is what happens, okay? This is in textbooks and so on. If you're ever interested in the original work, in Mohapatra, we showed this in 79. And we have a long paper in 81, which discusses this in detail. That's only if you wanted to understand more. But you are saying, I don't really care. I don't need the details of your new theory. I know that this guy is a singlet, so I will believe you. It can get a mass. For us, this is the main message. But let me just tell you then. If it is true, no, I won't say anything yet here. I will just remind you that means the Lagrangian for the right-handed neutrino looks like this. I, nu r bar. This is what Dirac tells you. We are looking at the free guys minus And it's interesting thing, look the way I'm gonna write, minus MR over 2, nu R transpose, C nu R. And there is a Hermitian conjugate, please, let's not forget. Now notice we said here nu R is actually, it's a 4-component spinner, but it's a 2-component spinner, strictly speaking. It's just a way of bookkeeping to 4-component, but this is 2-component. And you say, oh, but I don't know how to work with 2-component spinners because this is not how I write my Feynman rules and find my propagator. So what we do here, please pay attention, I can introduce a Majorana spinner. The fact that I'm taking a right-handed guy from the Lorentz point of view is irrelevant. The same thing would happen for the left-handed guy if he gets a mass. Lorentz doesn't care about left and right, okay? It's only the standard model. So this is now a fundamental thing we are doing at the moment. This is the, you are saying, why don't you do something smart here? Do this. Introduce a 4-component spinner. This is called the Majorana spinner. This is called, MR is called the Majorana master. And this is called the Majorana spinner. Let's see what I meant by this. Just to remind you, how would the Dirac, how did the Dirac typically spinner looks like? Dirac spinner looks like some left guy plus some right guy, and they are independent. This is the Dirac guy. This is a parenthetical remark. I'm interested in Majorana spinner. So this is nu R, psi Majorana is nu R, plus C gamma 0 nu R star. Nu R bar is, all I have to remember that nu R bar is nu R dagger gamma 0, and I get this. So this is nu R plus I sigma 2 nu R star. What is this? Well, let's write down. This is 0 UR plus 0 I sigma 2 minus I sigma 2 0, 0 UR star. This is the Majorana spinner. So what I get is I sigma 2 UR star, UR. I cannot overemphasize this. So it's a particle and antiparticle together, as we talked. Once again, I'm repeating this thing, but it's very important. Explicit. Now the homework for is to show the following: psi m bar gamma mu d mu psi m is 2 nu r bar gamma mu d mu nu r. I'm not going to do it. I want you to do it, and I will find the Lagrangian for nu r. It's simply 1/2 I psi m bar gamma mu d mu psi m, or it has 2 pieces, and you have to show that psi m bar psi m is nu r transpose C nu r plus Hermitian conjugate. This is the homework. So we get 1/2 outside, which is an irrelevant overall factor. Doesn't affect equations or motions, minus MR, psi m bar, psi m. It looks complete an analogy with Dirac. Satisfies the same equation. The difference, of course, is that in the Dirac case, there is no violation of lepton number. But in this case, notice I have together a lepton UR and then anti-lepton UR star. Therefore, I violate the lepton number by 2 units, as we said, but I can use the same mathematics and physics that I used before for Dirac. For example, I will have equation P slash minus MR psi m equal to 0. So MR is the mass, of course. So we call this a mass term. This is why I can call it a mass term. But notice I had this funny factor of half, and now I understand why I put the factor of half here. I had to do this little gymnastics to know what the mass is. You never know what your, be careful when you write the Lagrangians, okay, that before you are sure how your fields are normalized, you cannot interpret what the mass term is. Okay, because naively I would have said, oh, MR is the mass. No, it turns out that the half is the mass because the Dirac equation is the analog of the Dirac equation. In a 4-component notation, you always get the Dirac equation. In other words, that's the first thing. And the second thing is, of course, that the propagator, call it Majorana propagator, it's simply the same as the Dirac propagator. You have the same Lagrangian. This is irrelevant. As you know, an overall factor does not matter. The equations or motions are the same. You can forget about the half. So you have the same propagator. This is very useful. This is why I'm showing you this. The same Dirac-like propagator. So all you have to do is to write this in the 4-component notation. You can use all the rules that you knew and loved before. Of course, you can work with 2-component ones. People develop the rules for 2-component ones, and you can go and study them. It's very easy to redo it in the 2-component form. I just wanted to do this for those of you who are familiar, like me, with the 4-component notation and with Feynman's work. It's good to know that I can work, okay, equally. So I have the I have now the Majorana Dirac picture analogy. In the Majorana case, I have the following thing. I sigma 2 U star and some U, I call it UR. In the Dirac case, I would have, the difference would be that this would be completely different. UL would have nothing to do with UR. Everything else is the same. So this guy is a particle. The antiparticle is completely different. This guy is a half particle plus half antiparticle. So in this case, the Fermion number is conserved. Conserves Fermion number or lepton or whatever. If it is a baryon number, is conserved. Whereas here, if it is a lepton, you have delta equal to. If it is a baryon, you will have delta B equal to, if you do it for the baryon. Like neutron. You wouldn't write it for proton because it carries charge and so on. I think this is a good point to take a break. So we will. You see, usually my first part is longer, but that's okay. I need to sort of finish the line of thought. Please let me know anything you want to ask quickly. I think if there's something.
Yes, Professor, I have a question.
Please.
If we know that the Majorana term is invariant under the standard model symmetry, can we just add this term to the standard model theory because it's a singlet?
We could, precisely. In other words, we could say, and this is what I want to do now. This is a very good question. So we could say, okay, like what you are asking me. So there is a question. Can I forget about left, right, and just add new R with its mass MR to standard model? The answer is yes. And it is done most of the time. It is done basically almost all the time. And it leads to the, I want to talk about it, start at least today, to the seesaw mechanism. We can surely do that. You have a perfectly question. Now, what bugs me from the beginning, it would bug me. I would never do it like that. Because why should I introduce a right-handed neutrino? I mean, if I start introducing new particles, what is the logic? Which particle should I introduce? I mean, there are many other possibilities that could give me neutrino mass, and I can do it endlessly. Of course, yes, I can do that. And strictly speaking, in the neutrino sector, this is what happens. I will try to argue that the fundamental left-right symmetric physics will be very important. You will see why. And although I will argue that it's very important that this is perfectly, logically, physically, and mathematically allowed. When I say all the time, I really should say most of the time. We will gain something special when we go back to left-right symmetry. So let's do the following. We'll forget that there is any left-right symmetry. Maybe you didn't even follow. Maybe you didn't like it. Maybe you are happy with the standard model. Then let's just add, as you asked me nicely, let's just add the right-handed neutrino. Okay, look, let's meet at it's 4. Let's meet in 6 minutes. So they have a round number. Let's hit at 12:10. Please think if you have some other question. I'll be happy to answer questions and not move to new. Okay, 12:10, we are back. Any other question, please? I'm going to do precisely what you asked me. So I'm going to forget that there is a left-right symmetric model. So now what I'm told, what the left-right theory taught me, I just take the lesson that I have the standard model plus nu r. So let me ignore in the process, for the time being, ignore WR, the new gauge boson. Okay, let's just do that. And we say we have a standard model and nu r. Because why? Because we are studying neutrino, okay? Because we want to understand the physics of neutrino mass. So in other words, I have, let's forget the quarks. I have now this theory, nu EL, ER, but also nu R, which has a mass, MR. Remember, MR is coming. There is one lesson, however, very important, that I wouldn't have without the left-right theory. It's proportional to phi nu. And phi nu, of course, is much bigger than phi standard model, because this is very important. This, without the original theory of left-right, you wouldn't know. How do you know that? Because this gives the mass to WR, this gives the mass to WL, and you know that MWR is much heavier. Nobody noticed. By the way, let me give you the limit. MWR is bigger than about 5 TeV. It's really heavy. LHC has established, LHC is looking desperately for WR. Both CMS and Atlas are looking for WR. Both of the big detectors at the LHC. And now we know this is really impressive the way LHC is moving. It took us that we could have not imagined before. 5 TeV, you understand, this is 5,000 GeV. This is huge. So it's really huge. And this is maybe what justifies that I can forget the physics of WR for the time being. Just ignore it, you are saying it's very heavy. But what it tells me that I can assume, this is logical, that this is much bigger than MW. Coming from left-right theory. I'll take this message, because otherwise you will see I won't know how to proceed. This is very important. Okay, so now we go on. So when we wrote the Yukawa interaction in the standard model, remember how we wrote it? We wrote nu E L bar, Yukawa electron, phi doublet, ER. And then I can forget about the electron, right? From here I got the electron mass, but now there is also nu R. So I have to ask myself, can I write a mass term with nu R, a Yukawa interaction? Can I? I need your help now. We are building a new theory. I know that there is a master, and let me write it immediately, which I call them R. Nu R transpose, C nu R. I'm going to call it Yukawa-Dirac. I don't call it Yukawa-Neutrino, I call it Yukawa-Dirac. You will see why. You have to fill in here. What is here? This is your task, not mine. That's in the homework. I should be able to remember I did it for the up quark. Please go back and see what we did for the up quark. I should be able because nu bar is a doublet. It cannot be phi. See, question mark is not precisely phi. It cannot be because the hypercharges are different. Just to remind you, the hypercharge of ER is -2 and the hypercharge of nu R is 0. Just to remind you. But the bottom line is possible. So what happens from here? This is to be filled in. This is homework 4. There is nothing like doing homework, please. Reading what other people do is not the same. The point is that what I get is the following. I get from the above Lagrangian M E EL bar ER plus Hermitian conjugate. Remember ME, who remembers, is Yukawa E times, who's gonna remind me? V. I will also get that will be one term for the electron. I separate, I will get M Dirac, nu L bar, nu R plus Hermitian conjugate. And M Dirac will be obviously Yukawa Dirac times V. How do I know that? V is the only scale. Yukawa Dirac is the coupling. Everything in the standard model piece has to be proportional to V. But there is also 1/2 MR. This is very different. This is a crucial difference. You see, this is a profound lesson. This is what I got from the left-right symmetric theory. With MR, so I do have a lesson which is useful. It's much bigger than MD. MD is of order or smaller. I expect it to be smaller. MW, just like the electron mass, maybe even much smaller. We'll see. But it's coming from the same physics of the standard model. So this is very important. This is that. You see, strictly speaking, if you don't use the left-right symmetric theory, you don't know what MR is. Could be anything, could be 0, could be very small. Now I have a little problem. You see what I have a problem? I don't know how to proceed. I tell you why. I have a Dirac mass term here. So it's a funny thing. And here I have my Urana. So I don't really, it's sort of, it's hard for me to write really what is going on. I have some complicated mass terms. So instead of this, let's do the following. Let's go to Majorana or Dirac. We can do both. But let's go to Majorana kind of notation, Majorana way of writing, Majorana mass term. Majorana mass bows. Now, how can I do that? I do the following. Remember, if I have a fermion with some chirality, say FL, I can immediately introduce the fermion, which is C FL bar transpose, the charge conjugate. But this changes chirality. So if I have a fermion, let's be more specific, you are, I can introduce the fermion, which is NL C nu R bar transpose. Let me convince you once again that this is really left-handed. It's the same particle, notice. It's made out of nu R, but let's check it. This is C gamma 0 nu R star. We did it before. Remember, this is 0, I sigma 2, minus I sigma 2 0, u R star. Just want to make sure that you followed it. This is left-handed. An upper component is left-handed. So whether you like to work with nu R or nu L, it's up to you. You know why I want to work with nu L? This is better. Because our neutrino is left-handed. So now everybody is left-handed. Notice that I can write the following. Nu L transpose C NL transpose CNL. Let's see what we have from above is, what is NL transpose? This is nu R bar. C transpose. C. What is nu L? That's C once again, nu R bar transpose. What is this? C transpose C is 1. You can check it. Or minus 1, no 1. So this is nu R bar. No, why don't I write more elegantly? Why don't I go quickly? This is nu R dagger. Gamma 0. C. What is nu R bar? That's gamma 0. Nu R star. This is nu R dagger. Gamma 0 goes through, but becomes minus C. Gamma 0 square nu R star. So this is nu R dagger minus C nu R star. I can also write like this, nu R dagger, C dagger, nu R star. Because it happens that C dagger, which is equal to C transpose, is minus C. If you don't know this, if you don't remember it, then you must check it. These things you should be familiar with, but it's okay. Maybe you forgot, please check it. But remember how my mass term looked like. I had the following mass term, but I had a Majorana mass term, which was 1/2 MR. Then what did I have? Nu R transpose, C nu R, plus a Hermitian line conjugate. What is a Hermitian conjugate? That's nu R dagger, C dagger, nu R star. But look above, that's precisely NL transpose. So this is equal 1/2 MR NL transpose. I write the second CNL plus Hermitian conjugate. So as I said, where NL is just the other state is the antiparticle of nu R. So for example, the lepton number of NL is -1. And we like this notation N, just to remember that this is some neutral heavy lepton. It's not a neutrino. It's a very heavy particle. It is often called, you see, nu R is often called a right-handed neutrino, which is a very bad name in this picture. Often people say nu R is a right-handed neutrino. A bad name. It's not a neutrino. It's a very heavy particle. Neutrino is small neutron, you know, name, something very light, bad name. It's actually heavy. And it's some heavy neutral lepton. So N is a nice name for it. So in other words, Mn we can identify as Mr. It's the same particle. Because remember, actually, I do have particle and antiparticle always because of charge conjugation. Okay. I also have, remember, I have M Dirac term, which is nu L bar nu R plus nu R bar nu L, which I will write M Dirac nu R bar nu L plus Hermitian conjugate. But remember, I'm working with NL. See, once again, N is just C mu R bar transpose. So what do I have from here? I have that nu R bar is, no, why don't I write nicely? I can do better. I can do better than I wrote here. I have that NL is C nu R bar transpose. So from here I have NL transpose is nu R bar C transpose. And I multiply by C this relation. And I get that NL transpose C is nu R bar C transpose C, but this is 1. This is nu R bar. In other words, I get the M Dirac mass term as NL transpose C nu L plus Hermitian conjugate. And I write in a stupid manner, I write 1/2. No, I first remember, I show you something that NL transpose C nu L. I can interchange nu and N. This is minus nu L transpose C transpose NL because they anti-commute. And when I move it to the left, I'm taking the transpose of C. But C transpose is minus C. So this is equal to nu L transpose C and L. See, it's symmetric. My Rana mass type terms are symmetric in nu and L. So in other words, we have M Dirac So I can write 1/2 NL transpose C nu L plus nu L transpose CNL plus Hermitian conjugate. So what we get is the mass terms, now complete, plus 1/2 Mn NL transpose CNL. Plus Hermitian conjugate. Questions, please. By the way, you can easily generalize this. If there is more than one generation, notice that I have a factor 1/2, which is overall. I can just forget about it. It's just an overall thing, which has with the normalization of kinetic energy. I can think about it later, but in the mass terms, now you see the half disappeared nicely. If you have more generations, you will have NL transpose C M Dirac nu L plus nu L transpose C M Dirac transpose, of course, and NL plus NL transpose CMN NL plus Hermitian conjugate. Now, in this case, M Dirac, Mn are mass matrices. But this is just a passing comment, okay? I'll say a few words about generations on Monday, I guess. Just a passing remark. Let's forget it. Let's come back to it. For us, bottom line. Now we can summarize right now. I have a mass matrix, nu L, NL. It's a two-body system with a neutrino. We can call it N mass matrix. Looks like this. The first state is I write it in general and then we'll reduce it, okay? The first term is called between nu, here there is a 0. Nu, there is no mass term. This is forbidden by standard model symmetry. So this is very important. This is a very big 0. Nu L, NL, it's called M Dirac transpose. This is called M Dirac by definition. And this is Mn. We have a mass matrix. Which becomes for one generation, which we are doing always. We first do one generation, becomes the mass matrix nu n is 0, M Dirac, and some Mn. I write a capital letter just to remind you that Mn is big. Hope I'm not confusing. There is no matrices. And this is nu L, NL, nu L, NL. I have to write these two states because I have to do what now? I have to find out which are the physical particles. Which are the physical particles? How do I decide which particles are physical?
We find out the eigenstates of the mass.
Eigenstates, right. The physical particles. You see, nu and n are not really physical states. The physical states are eigenstates of the above matrix. And that will be very easy, but we first have to find the eigenvalues. I can go and diagonalize to find the eigenvalues, but I can find the eigenvalues very quickly in this following approximation. Let's see if you can tell me at least one eigenvalue in this approximation. It's a very ugly matrix. Well, not so ugly, but the eigenvalues, you know, you get a quadratic equation and the eigenvalues are a bit complicated some. But we are assuming this in this approximation. What are the eigenvalues?
One of them must be Mn.
One is Mn. In other words, there is a heavy state with a mass, let's call it M heavy, which is roughly Mn. Right? Because the correction will be very small because M Dirac is very small. What about the light state? We'll have the, or light state, like, you know, large. I'm talking about eigenvalues. So this is not the way I go. Let's say the large mass. And what about the small mass?
It should be md square over Mn. Because
Yeah, very good. How to reason the trace. So let's answer it. Very good, you got it. We know the trace of M nu n is Mn. Determinant of M nu n is, what is the determinant?
minus md square.
Minus, let's keep this sign. It's just a sign, but let's keep it in mind. This, as you know, is the product of, this is the sum of the two masses, and this is the product. And one mass is much bigger than the other. You just told me that M heavy. So let's say that let's say the following, that M1 is what I called M heavy. I shouldn't write, let me just write small letters, but M heavy. Small mass. So small mass, let me be very clear, which is M light. What is M light? Well, I know now M1 is M heavy, and that's roughly Mn. And I know that M heavy times M light is minus M Dirac square. And from here, M light is minus M Dirac square over Mn. Why don't I write? There is a minus sign, which is a detail. The important thing is notice that in the approximation, this is true only if MD is very small compared to Mn. This is called the seesaw formula. And it's valid only in this approximation. It's called the seesaw. So you have a seesaw, you have a big guy here, which is N sitting here. And it gives a, you know, we have our little guy nu, and N gives a mass to nu. You see what happens when M Dirac is 0? So in the limit, notice immediately limits. If Mn goes to infinity, this is the standard model picture. You get that M light, which we called M nu. I should have called this. This is identically, this is of course identically M nu. Because what happened is neutrino was massless, but then it mixed a little bit. You see, it mixes a little bit to N. And so by mixing a little bit through this term, that picks up this huge contribution of n, it gets a little mess. So the standard model limit is mn going to infinity, and this you get immediately 0. So you should think of the standard model, where did the guys make a mistake? Kidding, of course, because they wrote the minimal theory of the visible particle, is you should never take the limit of n going to infinity, which is the scale of U physics, okay? And this is what I want to tell you. I would not forget, if I were you, that there is actually a theory behind n, because I may discover something very important. Also, of course, if m Dirac is 0, so this is A, and B, if m Dirac is 0, even if n has a finite might but doesn't couple to our neutrino, then who cares? It's some phantom particle. You will get again that m nu is 0, which will be the standard model. In the standard model, neutrino is not coupled to anybody else, okay? So this is the standard model limit. This is now why we can say that neutrino is massless in the standard model. But the crucial thing is that m neutrino is minus m Dirac square mn is of the order of m Dirac times minus m Dirac over mn. And this number is much smaller than 1. So you see, a natural thing would be that m Dirac is of order of mn. The electron, they live together. After all, neutrino and electrons are siblings. And the seesaw mechanism helps you understand that why neutrino is much lighter than electron, even if they had similar m Dirac. This became now kind of the canonical way this has won over. This became kind of the scenario for small m nu. We have to talk about it tomorrow at length. I will ask you now if you have any questions. Oh, I hate this. We have a big, heavy guy and the tiny. This is the name C. So notice, however, that I tell you just once again that I know why neutrino is light. But look, if I just take standard model plus n, which was really nu r or nu r star, then I have a question. What is mn? I have no idea. I don't even know what to relate to. And I have no idea what m Dirac is, strictly speaking. It's an independent mass term. So the seesaw mechanism apparently tells you why neutrino is light, but it sheds no light on m nu. You see, it's not really true that we are explaining why neutrino is light. We are really writing this. Mn is minus m Dirac square over m nu. This is what you measure. And then you're saying that there is some heavy guy there, but you're not doing the opposite because you have no idea what n is. You don't even know how to find it. The guy is some crazy guy that is completely phantom-like and just couples to our little neutrino, which is very hard to see anyway. And I don't even know what m Dirac is. The army of people are working on the seesaw mechanism, okay? And you know, I feel a little bit like Dr. Frankenstein of creating a monster. I'm one of the people attributed to whom this is attributed. To me, this per se tells me nothing. This I have to deduce, but in order to deduce it, I will have to know what m Dirac is. I cannot make a single prediction. It's not good to claim that you have an understanding of some phenomena without making physical predictions for new processes, okay? To me, this is not good enough. And I want to tell you a little bit of why I insist on this and why it's important for you and I to understand how to somehow make this a theory of neutrino mass. Because look, this I can say, however. Remember, yesterday I told you Weinberg says, whatever you do, you will have mu to be v square of other lambda. Remember, we called it lambda Weinberg, a new scale. mu. Weinberg says doesn't matter which theory you come from. The seesaw guy says what we say mu is m Dirac square. Forget the, let's take the absolute value. Mu is m Dirac square over mn. M Dirac is Yukawa Dirac square v square over mn. So all we are saying that one of the lambda Weinberg is Yukawa Dirac square over mn. We have traded the Weinberg operator for mn. However, this is a very important point, by the way, which Weinberg is missing, that Yukawa Dirac much smaller than 1 is natural. In other words, it is natural that mn is much smaller than lambda Weinberg. While the Weinberg is not right when he claims the scale must be large, that's all. But his language is better. Because if I don't know what Yukawa Dirac is, then why use if Yukawa Dirac is not predicted and mn is not predicted, then Weinberg effective language. I'm sorry, I just have to finish on this note. Effective language is better, in my opinion. Just like Fermi language is better if you have no theory of W boson or decoupling. It's always better to use an effective language when there is no true theory. Or we try to have a complete predictive. And I will stop here. Predictive. Let's say self-contained, that you don't add anything else. Contained theory. We knew phenomena, processes. Then, of course, we should claim that we have a theory of neutrino mass, but not just to rewrite Weinberg through some fictitious particle, okay? We need, what I'm trying to say today, we need the analog of standard model, but for neutrino, a real theory. Questions? I'm finished. I took a few more minutes, but forgive me, but I needed it. Questions?
One question. So we have seen like the physical states of neutrinos was from the linear combination of the new L and NLs.
Right. We have to. Yes, very good.
And basically, L comes from the extension of standard model where we include the right-handed neutrinos.
Right.
So if we just think about some physical neutrino having some interaction, so that means we will have some right-handed kind of interactions also, because physical neutrino is basically a combination of left and right-handed
Yeah, very good. Very good. What you're saying, let's discuss this tomorrow. This is really to open up a discussions for tomorrow. You are saying neutrino is not just nu L, but there is a mixture. It will be from here, right? Let's go back to our matrix. Since you ask, that will be a small mixing between nu L and NL, which is of order. There is some epsilon. Let me write. And N new state will be NL minus epsilon UL. What is epsilon? Can you guess immediately?
MD over Mn.
Right. We must go to 0 when Mn goes to infinity, or Mn to go to 0. Okay. So it's a small number, much less than 1. So in other words, when I write the interaction nu L gamma mu EL, it's not really right-handed. Don't think in terms of the chirality, because I don't have to work with right-handed neutrino. I told you, think of N, which is left-handed. This is G over square root of 2. Nu L now is nu bar, and nu L is a little bit mixture of N. This, of course, couples to W mu plus, so it couples to W mu plus. So we have a new interactions, you are saying. G over square root of 2, epsilon, NL bar, gamma mu, EL, W mu plus. You see, this is sort of exciting. You are saying, look, I have a new interaction. Goran tried to cheat me. And I could, in principle, maybe try to produce this guy. Can I produce it? The trouble is that the cross section to produce N, sorry, this is not NL, this is N. Physical states are nu and N that I called N. It's not so much chirality, it's just to get the new interaction. I think this is what you meant, right, in your asking me. Notice it will be proportional to epsilon square. But epsilon square, notice we have to take these few minutes because you ask a very important question. It's m Dirac square over mn square. Agree? You agree with me? Everybody, I hope. But go back to what m nu is. M nu is m Dirac square over mn. So this is m nu over mn. But remember, we said that Mn in the seesaw picture is much bigger than Mw, which is 100 GeV, which is 10 to the 11 electron volts. And we know that M nu is surely less than 1 electron volt. In other words, the cross section to produce N will be suppressed by 10 to the minus 11 times the usual weak interaction. This is 0. So N really is a phantom particle. It's crazy to talk about it in the seesaw picture. If you like the seesaw picture that you claim, I have a beautiful understanding of why neutrino is light because then it's heavy. By the same time, you are, shooting yourself in the leg. Well, you are doing, you're really killing yourself. You're saying, oh, but I can never produce it. It's going to be 100 years or something. So this is one of the main reasons why I personally wouldn't work. I mean, it's boring. Because you cannot produce it, so you can say anything you want. You can write a lot of papers. It's very easy to write papers of something that you cannot see. We'll elaborate on this even more. Any other question? I know it's getting late, but just in case there are questions. Those of you that I'll come back to this. Even if you don't ask me, but especially if you ask me. All right. If there are no other questions, let me do this immediately. Otherwise, I may forget. I'm exporting this. You can ask some questions. I will not write anymore. Oh, by the way, we tomorrow maybe we should talk about it. Is that it seems that majority wants a take home. So you guys should try to talk to each other. I don't know whether you meet or so on, or write, but write so that everybody can see it, your preferred dates for the exam. What did I do? Anyway, I don't know if I sent. Well, it seems not. Okay, I'll do it. Think about the, I'll bring it up tomorrow. I'll bring it up tomorrow. We will have to decide. It's going to be a take home, it seems, by popular vote, by democracy. I'm sorry for those of you who don't like the idea, but we have to, you know, that's the best we have. You know, the democracy has many faults, right? But okay, so think about the dates, please. And when you have some ideas, just write it, you know, on so that all of us receive it. Just reply all. Okay, take care. I'll see you tomorrow.
Thank
Thank
you.
you.
Bye.